In this video, we're going to discuss the gas laws. So there are 4 laws we're going to talk about: Boyles Law, Charles Law, Gay-Lussac's Law, and Avogadro's Law. And we are going to go over these individual gas laws, and then the next video, we are going to combine them into the ideal gas law. But it is good to look at each of these laws individually. It kind of simplifies things down. And you're only dealing with 2 variables instead of 4 variables like you are in the ideal gas law. So we're going to kind of ease ourselves into talking about gases and how we quantify and look at what happens to a gas when its conditions are changed. So before we go into much detail, I do want to just kind of give you some background information. Some of this we've covered in class. Most of this we've already covered in class. Many substances we interact with here on Earth at normal temperatures and pressures exist as gases. So Earth's atmosphere is 78% nitrogen gas, and it has 21% oxygen. The oxygen is necessary for us to exist, right? Our lungs breathe in oxygen. We breathe in the air in our lungs. The oxygen is absorbed into our bloodstream. And we need oxygen to survive. So we interact with these gases on a daily basis, especially Earth's atmosphere. 1% of the atmosphere is other gases and particulates, but that's just one example showing that we interact with gases all the time. Under ordinary temperatures and pressures, most gases behave similarly. So whether it be nitrogen gas, oxygen gas, fluorine gas, they will behave similarly. So that means we can kind of just model them as a gas with ideal behavior. So this helps simplify things down for us, and we can model gases. Since gases mix together, we model them just as a gas. Of course, gases don't always act exactly ideally, but we're going to make the assumption today that gases are ideal when we do these calculations. So what do we mean by that? Well, an ideal gas is a hypothetical gas whose particles occupy negligible space compared to the space between them. Okay, you can see over here in the diagram that these particles are small in compared to the space between the particles. Okay, it looks like most of that container is made up of empty space. So that's what we mean by occupy negligible space. We also say that these gases will undergo perfectly elastic collisions. So that means when they hit each other, they're not going to lose any energy. They'll just fly off in a different direction with the same amount of energy. We also say that the particles will move in straight line motion and are not attracted or repelled toward each other. So they're going to move in a straight line until they hit the side of the container or hit another particle, and they're not going to like veer off course because they're attracted to another particle in the gas. What quantitative data can we gather about this gas? Well, you'll see over here in the video that we have a thermometer. We can measure the temperature, the pressure, the amount of gas, and also the volume of the gas. So amount we would measure in moles. Temperature, when we deal with these gas laws, we have to put temperature into the absolute temperature scale, which is the Kelvin temperature scale. So if you recall, 273.15 Kelvin is the same as 0 degrees Celsius. So if you're trying to convert a temperature from Celsius to Kelvin, you're going to have to add 273.15 to that value in Celsius. We can also measure the volume. Typical volume measurements would be in liters or centimeters cubed when we're dealing with these gas laws. And then pressures are going to be in atmospheres or kilopascals. So kPa for kilopascals or ATM for atmospheres. I'm going to go in a little bit more detail about pressure and measuring gas pressure because we have not yet discussed that as much in class. But we kind of have an intuitive sense of what pressure means. When a gas is in a container, it's going to exert a force on the sides of that container due to the gas particles colliding with the walls of the container. Okay, So pressure is actually equal mathematically to the force that all those little particles exert on the sides of the container divided by the area. Okay, so you can take a little portion of a wall of the container, or you can look at the container as a whole. You should get the same pressure, okay, throughout. So what are the units of pressure? Well, the unit of pressure that we're most common, that is most common to us, is probably PSI, or pounds per square inch. In this table here at the bottom, I have a column for standard pressure. When we look at gases, sometimes we refer to standard temperature and pressure. And standard pressure is going to be the pressure at sea level. So looking at the pressure at sea level, it's going to be 14.7 psi, that atmospheric pressure. And in the units of pounds per square inch, we could draw a circle in the sand down here that's 1 inch square, and that column of air above it that is applying a downward force on that 1 square inch circle that we've drawn on the sand, that's going to be 14 pounds of air, okay, in that column. So that's kind of, if we visualize what that 14.7 psi means, it means that at sea level, that column of air above an inch square is gonna be 14.7 pounds. With the gas laws, though, we're not going to be using PSI. We're going to be using either pascals, okay, or atmospheres. Atmospheres is a very intuitive way to measure air pressure, because 1 atmosphere is equal to this 14.7 psi, or this air pressure that you feel at sea level, or the air pressure that exists at sea level. So the first one of these laws that we're going to take a look at is Boyles Law, and Boyles Law relates pressure and volume. Okay, it relates pressure and volume when you hold the temperature and the amount of gas the same. Okay, and what Boyles Law tells us is that the pressure of a gas varies inversely with its volume. Okay, when that amount and temperature of the gas remain constant. Mathematically, that looks like P1 V1, or the initial pressures and volumes of a given scenario, are going to be equal to the product of the final pressure and volume. So P1 V1 equals P2 V2. Graphically, okay, this would look like if there's a certain given pressure at a relatively low volume, if you were to increase that volume, the pressure must go down. Okay, and that's due to the fact of this relationship here that multiplied together, they're going to equal a constant. Okay, so you would get some sort of curve. If you increase the volume further, that pressure is going to go down even more. So if you were to plot multiple points, you would get a relationship that looks like this, and it's an inverse relationship. Okay, as you increase the volume, pressure goes down. Okay, if you were to increase the pressure, the volume goes down. Okay, this first gas law is Boyles Law. I'm going to attempt to demonstrate Boyles Law, the relationship between the pressure and volume of a gas, while you hold the amount of gas and the temperature constant. So I'm going to put the lid on to keep the amount of air inside the water bottle constant. Then I'm going to attempt to decrease the volume so much that the pressure exceeds that the cap can handle, and the cap flies off. Okay, here we go. Okay folks, I don't think my original plan is going to work. The bottle cap seems to be stronger than my forearm strength. So I'm going to attempt to open it and just right at the last second kind of twist the cap a little bit, and we can see how the cap flies off due to the pressure that is built up inside of the bottle. So that's the new plan, because the other plan failed dramatically. So if we take an initial given amount of gas and we decrease its volume, that pressure is going to go up. Okay, and if we take the volume and decrease it even further, we're going to get a pressure that goes up all the way to 2.1 atmospheres. So the reason for this is as you decrease the volume, those particles are going to be hitting the sides of the container more often, and there's more force per unit area because they're hitting the wall more often. If we were to then increase the volume by pulling and making the container larger again, then you'll notice that the pressure over here on the pressure gauge goes back down. Okay, let's take you through an example problem that you might see of Boyle's Law. So the problem statement here is if the volume of a closed empty bottle, okay, with a pressure of 1 atmosphere is decreased from 1 liter to 0.33 liters, what is the new pressure of the air in the bottle? And this is a Boyle's Law problem, so we assume that the temperature and amount of air inside the bottle don't change. So this is similar to what you saw in the example, the real life example. You take the volume and you decrease it. That pressure we expect to go up. So the first thing I do in all of these problems is I take an inventory of what variables I have and which one I'm trying to find. So my initial pressure, P1, is 1 atmosphere. Initial volume is 1 liter. Okay, the final pressure, that's what I'm trying to find. And the final volume I do know is 0.33 liters. Okay, so now that I know my variables, I'm going to write down my equation and rearrange it for what I'm trying to solve for, which is the final pressure, or P2. So my P1 V1 equals P2 V2. What I need to do is I need to divide both sides by V2 so that I'm left with P2 by itself. Okay, so that gives me this equation that P2, okay, because this V2 cancels with that V2. So my P2 is going to equal my initial pressure times my initial volume divided by my final volume. So plugging in the numbers, I get 1 times 1 divided by 0.33, plug that into my calculator, and I get that the final pressure is 3.03 atmospheres. Okay, good news, it did go up. That's what I expected. So that is how you would solve a Boyle's Law problem where you're solving for the final pressure. Okay, the next law we're going to look at is Charles' Law. And Charles' Law was actually developed quite a few years after Boyle's Law. So we knew about Boyle's Law for a while, and Charles was actually looking at Boyle's work and realized another relationship, and a relationship between volume and temperature. So he found that the volume of a gas is directly proportional to its temperature. And that holds true as long as you're keeping the amount and pressure of the gas constant. So the mathematical relationship is that the initial volume divided by the initial temperature is equal to the final volume divided by the final temperature. A very important thing to note here is that these temperatures must be in Kelvin. So when you plug these numbers in, must be in Kelvin. Okay, well, let's take a look at what this looks like graphically and what does a direct relationship look like. So if we take an initial temperature and plot its volume and then increase that temperature, in order to keep this V1 over T1 same ratio, your volume must increase. So basically what this direct relationship tells us is that if we increase volume, temperature increases, or if we increase temperature, volume is going to increase. So when we plot our temperature, our volume versus temperature, we get a straight line. And as one increases, the other also increases. And the vice versa, it's true. If you decrease the temperature, the volume will decrease as well. And remember, this is in order to keep the pressure constant with a certain amount of gas. Okay, second gas law we're talking about is Charles' Law. So Charles' Law relates volume and temperature, while pressure and the amount of gas stay constant. So I have kind of smashed a water bottle here, closed the top. It's about room temperature right now. It's 68 degrees in here or so. So we're going to go ahead and place this over the top and kind of into the boiling water. And as that's happening, you will hear the cracking of the plastic and the air inside is heating up. And as it heats up, it increases in volume. So we'll just sit here and watch it. We get a close up. There we go. My hand's kind of in the way. There we go. But it's almost back. It was pretty smashed before, and now it's pretty much all filled again. Cool. So that's Charles' Law. Okay, so if we wanted to take a look at Charles' Law, okay, if we were to plot an initial volume due to its temperature and then were to increase that temperature, we would notice that the volume needed to be increased in order to maintain that same pressure. Similarly, if we were to decrease that temperature down, then the volume is also going to have to go down to maintain that pressure. Okay, an example problem that you might see for Charles' Law. So in this example, it asks you to calculate the increase in volume of a 0.5 liter 0.5 liters of gas in a sealed container at 20 degrees Celsius. Okay, and in parentheses, I put Kelvin to remind you that all of these problems need to deal with temperatures in the absolute temperature scale, which is the Kelvin scale. And you're heating that sealed container to 100 degrees Celsius, and there's no change in pressure. Okay, so just like we did with Boyles Law, the first step is to inventory your variables. So our initial volume here is 0.5 liters. Initial temperature, I write it down in Kelvin, 293.15 Kelvin. Okay, the final volume is what we're trying to find, and the final temperature converted into Kelvin is 373.15 Kelvin. So remember, the way I got this number is I take whatever I have in degrees Celsius and add 273.15. Okay. Next thing, I want to write down my equation and then rearrange it so that I can solve for that final volume. Okay, so in my equation, what I'm going to need to do to get V2 by itself is I need to multiply both sides by the final temperature, or T2. Okay, so I'm going to multiply both sides of this equation by T2, and that's going to give me an equation that solves directly for the final volume. And it tells me that I'm going to need to take the final temperature times the initial volume and divide by the initial temperature. Okay, plugging those numbers in, it looks like this. And then when we solve that, we get that V2 equals 0.636 liters. Okay, oops, it's popping up at the bottom, sorry. So we get 0.636 liters, but that's not what the question was actually asking. It was asking the increase in volume. So I'm going to need to take 0.636 minus 0.5, which was that initial, to give me that change or that increase. So there's an increase of 0.136 liters in order to maintain the same pressure when we heat that container from 20 degrees Celsius to 100 degrees Celsius. Okay, the next gas law we are going to investigate is Gay-Lussac's law. And Gay-Lussac's law, for Gay-Lussac's law, we're keeping volume and the amount of gas constant and looking at how pressure and temperature change. So if we increase the temperature, keep the volume of gas the same, we kind of intuitively know that this is going to increase the pressure. Okay, so we get a mathematical relationship that looks very similar to Charles' law, but we have P1 over T1 equals P2 over T2. Same rule applies when you're plugging in temperatures. They must be in Kelvin here. So graphically, we have a direct relationship again. So as you increase temperature, that pressure is going to go up. Okay, and if we were to graph a series of data points, we would get something that looks like this, a straight line that indicates a direct relationship that as one increases, the other does as well, or if you decrease one, the other must decrease to maintain the volume. So for this real world example, I don't have a fun video that I made. We're just going to talk about aerosol cans. So you will notice if you look at any aerosol can, like spray paint, anything that you're going to spray from an aerosol, that it says keep away from heat. So those aerosol cans have pressurized gas in them, along with the liquid that will either aerosolize or be sprayed out in a foam of the can. So there is some gas in those cans. So if you set that can near a heat source, let's say you have a wood stove or something in your shop, and you set that aerosol can next to the wood stove, that gas is going to increase in temperature, and because it's in a sealed container, the volume is going to stay constant. So what's going to happen is that pressure goes up and up and up, and it can be very dangerous because they can explode when the pressure reaches a certain point. Okay, so looking at a simulation of Gay-Lussac's law, if we have a given initial temperature and plot the pressure, and then we were to add heat to the system, maintaining that volume constant, you'll notice that the pressure goes up. Okay, this pressure gauge is going up and up and up as we increase that temperature. Okay, as the temperature goes up, those molecules or those particles move around faster, so they're hitting the walls more often. If we were to then decrease the temperature back down, we will notice the pressure is going to head back down as well. So as that temperature is being decreased, the molecules move around slower and slower. They're hitting the walls less frequently. There's less force on the side of the container, and so our pressure goes down. Okay. Okay, what would an example problem for Gay-Lussac's law look like? Well, we have a rigid tank in this problem filled with 25 degrees Celsius gas at 2 atmospheres. Okay, the tank is sealed and then heated until it reaches 3.5 atmospheres. The question is, what is the new temperature of the gas? Okay, so what temperature do you have to heat it to get to those 3.5 atmospheres? So, same steps that we've been doing. We're going to inventory the variables. Our initial pressure given in the problem is 2 atmospheres. Initial temperature, again, we have to convert 25 degrees Celsius into Kelvin. So we add 25 plus 273.15 to give us 298. I rounded it to 1 decimal place because of significant digits here. Our final pressure, we do know, is 3.5 atmospheres. And that final temperature is what we are trying to find. Okay, so then I write down my equation, and I'm going to rearrange it so that I get an equation that says T2 equals something. So my Gay-Lussac's law, P1 over T1 equals P2 over T2. I noticed that my T2 is what I'm trying to solve for, but right now it's in the denominator, which is not what I want. So I'm going to actually multiply both sides by T2. That's my first step to get T2 in the numerator. Okay, so that gives me T2 times P1 over T1 equals P2. That's not what I want. That would be an equation if I was trying to solve for the final pressure, but I know the final pressure. I want to have T2 by itself. Okay, so I'm going to need to divide by P1 and multiply by T1 in order to get T2 by itself. So I can do that in one step here. And I get my equation for T2. Okay, so again, this P1 would be canceled out here, T1 canceled out here, and then this gives me my equation down here, P2 times T1 divided by P1. Okay, taking my numbers and plugging them in, I get 3.5 is my final pressure times 298.2, my initial temperature, divided by my initial pressure, 2, and plugging that into a calculator and solving, I get 522 Kelvin, or if I were to convert that back into degrees Celsius, it would be 249. Okay, so the last law we're going to talk about is Avogadro's law. And Avogadro, we've heard of him before. Okay, he is the mole guy. So Avogadro's law has to do with the amount of a gas and its volume. So Avogadro's law is that when the volume that is occupied by gas is directly proportional to the number of moles of gas if you hold the pressure and temperature of the gas constant. Okay, so his relationship looks like this. And again, that's a direct relationship. So the initial volume divided by the initial number of moles is going to be equal to the final volume divided by the final number of moles, as long as that pressure and temperature has remained constant. Graphically, like all of these direct relationships, you're going to get one variable increasing as the other increases. So you get this straight line of a direct relationship. Okay, where as volume, the number of moles increases, the volume increases. If we were to decrease the number of moles, the volume would decrease. Okay, so this beach ball does not contain a lot of air right now. Okay, so it does not take up a lot of space. But what happens if I add more gas molecules to the beach ball? Okay, so as you can see, as I added more particles of the gas, the volume of the beach ball increased. So that's a very simple demonstration of Avogadro's law in action. Okay, so when we look at a simulation of Avogadro's law, you will notice I'm increasing the number of particles or number of moles in this container. And each time I do that, the volume needs to increase in order to keep this pressure and this temperature constant. Okay, so Avogadro's law, again, is just saying that in order to keep pressure and temperature constant, if you increase the moles, you have to increase the volume. Or if you decrease the moles, you have to decrease the volume in order to maintain those two things as being constant. If we take a look at an example problem for Avogadro's law, here is one where you have 1 mole of helium gas that occupies 22.4 liters at standard temperature and pressure. So remember, standard temperature and pressure is 0 degrees Celsius, which is 273.15 Kelvin, and 1 atmosphere. Okay, the question here is how many moles of helium gas are there in a 1,020 liter container if the contents of that container are also at standard temperature and pressure. So again, we inventory the variables. So our initial volume in this case is 22.4, and we have 1 mole of gas to begin with. Okay, in the second container, or the second condition, we have 1,020 liters of the helium gas, and we want to know how many moles there are in that container if both containers have the same temperature and pressure. So we write down our equation for Avogadro's law. We have V1 over N1 equals V2 divided by N2. Okay, we're going to need to multiply both sides by N2. N2 is what we're going to be solving for, but right now it's in the denominator. So we want to get it up in the numerator so we can multiply both sides by N2. That pops the N over to the other side. So here's our revised equation, but we're still not solving for what we're trying to find. If we were trying to find volume, this would be a great equation, but we're trying to find the final number of moles. So we need to do one more step, divide by the volume and multiply by the initial moles. So we get an equation that our final moles are going to equal final volume times the initial moles divided by the initial volume. Okay, when we plug our numbers in here, we get 1,020 times 1 divided by 22.4, and that works out to be 45.5 moles. Okay, so at this point in the video, we've been through all 4 of the gas laws that we are covering and done example problems of each. You've seen a real world example of each. I do have some additional practice problems if you're looking to do some more problems like this in practice. Here are 3 more problems you can do. The answers to these will be in the description. But thanks for watching, and next week we're going to actually put all these concepts together and look at the ideal gas law.